So urgent models take the whole network as a whole and try to estimate what combination of parameters makes a network that looks like the real network we observe the most likely in terms of all these summary statistics. But this is a very sort of macro view. It does not explain much about which country connects to which country. It only explains how do we get a network that looks like the network we have in terms of the number of ties, the similarity between nodes that have ties, and so forth. The SAOM model, the stochastic actor-oriented model, takes the opposite approach. It looks at this network from the perspective of individual actors, and it makes the underlying assumption that it is actors that decide whether or not to make ties with other actors. And it tries to explain this on the basis of features of the network and features of the actors and features of the ties of these actors. So it takes a very local perspective. The unit of observation where it zooms in is the local node, not the network as a whole. But it similarly tries to then estimate the likelihood of ties for any particular node, given where it is located in the network, the values on other external variables, the values on these variables for neighbors, and so forth. It also is a great framework if you want to investigate the interaction between node changes and network changes. So for example, if a country makes a transition from a non-democracy to a democracy, it changes where it is placed in the network. It will change how likely it is to trade with other neighboring units. But this trade might also affect whether a country is likely to become democratic or not. So this kind of interaction, this kind of co-evolution refers to node features changing and tie network features changing, and they affecting each other, can be modeled much more easily with SAOM than with URGEM. So SAOM makes a number of assumptions. First of all, it really requires longitudinal data. It requires observing the same network over time. Yeah? Now, there is a variation where we can estimate a SAOM for only one case, and there's a recent paper by myself, currently under review, that investigates that type of model. But generally speaking, the basic idea is that we have longitudinal data, the network observed over time. And we assume that it is the individual nodes that can decide on making ties or not. So the formation of ties is driven by the nodes. It's a behavioral model. We assume that these changes can happen anytime at any point in time. So not year 1, year 2, year 3, but any particular time in between year 1, year 2, etc. So it is a continuous version of time, a bit like survival modeling and not like how we did time series modeling. It assumes that big changes in the network are based on small changes in the network. So if there is a large change from T1 to T2 in terms of which nodes have ties and which don't, we assume that between T2 and T1 there were lots of small changes where every time one agent made one change that then led to this overall big change. And we assume that each of these changes always take into account the network at that point in time, but not the network in previous points in time. So these actors, when they decide to make particular connections or not, they do that on the basis of what the network looks like at that point in time, not taking into account the history of the network until that point in time. And finally, it's a statistical model, so we assume that there is always random noise, just like an error term in a linear model. There are changes that are structural that we model, and there are changes that are stochastic, that are random. And based on summary statistics, now these summary statistics, they are similar to in URGEM. They look at triad formation, similarity between neighbors, and so forth, but they are now always calculated with this subscript I. They're calculated separately for each of the nodes. So they always take a local perspective, whereas in URGEM, these summary statistics were always calculated for the network as a whole. That is the big difference between URGEM and SAOM. In SAOM, we calculate all these summary statistics for the individual node, and then we associate parameters, in this case called theta, with each of these summary statistics. And then we can look at which of those parameter estimates make the changes that we observe in the network the most likely. And we have two regression equations rather than one. One that affects how likely it is for any agent to make a change, which we call the rate function, and a separate one which explains if there is going to be a change made by this actor, what kind of change is the most likely. Yeah, so one drives whether or not agents make changes, the other drives what changes they make. And like with log odds, like with URGEM, we are not comparing the network or any change against all possible changes, we always compare the network as it is to the network with one minor change made. And then we can look at the log odds, we can look at how likely is it to make the change, how much does it improve the likelihood of the data if that one change is made. So the rate function has underlying an exponential distribution because it's always positive, and it drives when agents are allowed to make changes. Yeah, so it can be low, then between two different discrete time periods there are very few changes, or it can be high, and between these different discrete time periods there are many changes. And each change is always a small change. It's one actor changing one tie or one node attribute. So here we see an example of the output of a SAOM model based on a friendship network, so from sociology. This model is invented by sociologists. So you see parameters for the objective function and parameters for the rate function, and you see parameters that relate to network changes, changing ties, and parameters that are referring to behavioral changing features of nodes. So for example, the coefficient on out degree is negative. That means that people that have few friends are also less likely to make friends. The feature on reciprocity is positive. That means that if I make a friend with somebody else, that person is more likely to treat me as a friend as well. The coefficient on transitive triplet is positive. This means that if I make friends with A and also with B, then A and B are more likely to become friends. It shows that the sex for ego is a positive coefficient, so it means that men are more likely to make friends. Yeah? The sex for alter is also positive but lower. That means that men are more likely to have people become friends with them. But this coefficient is insignificant, right? So we have a coefficient 0.19, a standard error of 0.16, so that is an insignificant effect. So when we think about the ego, me, making friends, men are more likely to make friends than women. If we think of the gender of the person that is befriended, gender matters less. So similarity between two individuals in terms of delinquency increases the likelihood of friends. Delinquents are likely to befriend delinquents, non-delinquents are likely to befriend non-delinquents. Yeah, so that is sort of the coefficients on the objective function for the network. Look at the network rate function. We can see that men are less often making friends. Yeah? And average similarity has a positive effect, so the more there is a certain clustering effect in the data where units that are more alike in terms of making friends, they are also more likely than to often make friends. Yeah? So the frequency of changing friendship ties is clustered, and there are clusters in the data of people that frequently change ties, and there are clusters in the data of people that less frequently change ties. This is what the average similarity here indicates. So if we think about this kind of spatial econometrics perspective, and you remember that we have this rho W Y, which was about how much neighbors influence each other in terms of node attributes. This can also actually be modeled in a SAOM context, the same kind of spatial diffusion of node attributes. And the summary statistics that are most relevant there are average similarity and average alter effect. In both cases, it's looking at clustering of node attributes among neighboring nodes. So a current working paper that we have shows that if the data generation process, remember the video on Monte Carlo studies, if the data generation process assumes there is a spatial econometric pattern, spatial autocorrelation, and we use the SAOM network model to try to estimate the extent of this spatial similarity, it does reasonably well. So we can use SAOM to estimate spatial econometric questions as well. And as I said, SAOM works particularly well with coevolution, where we try to model both changes to the ties and to the nodes simultaneously and look at how these changes impact on each other. So SAOM is a very versatile type of model. It can model network changes, it can model behavioral changes, and it takes the network into account when it models behavioral changes, and it takes behavior into account when it models network changes. So it's a very versatile model to try to understand these kind of complicated network interdependencies in the data.